What takes more energy? Melting a solid or boiling the corresponding liquid?
Boiling.
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 Boiling takes
Boiling.
more. Boiling takes
Why? Because it's a higher temperature?
Because
I don't
a
know, I
thing
just
has
remember.
like higher specific heat.
I don't know, I just remember the value of higher.
Think of what's happening to the particles. When something melts, what's happening to the particles? They're kind of stuck in their position, and then they start being able to move around each other. They have more kinetic energy, so you have to put heat into it to get them to move faster. When you're boiling the liquid, you're taking particles that are still real close to each other and doing what with them?
Spreading.
You got to completely break them apart from each other. And why are they in a liquid in the first place? Because they're attracted to each other. So you have to break those attractions of the particles from each other. Always takes more energy to boil than it does to melt for the same substance. So it's the same exact calculation for boiling, except that the constant value that you use is different. We use the heat of vaporization.
That's like I did it last time. I just made it. Yeah, thank you. Yeah, I know you were.
For water, the heat of vaporization is quite a bit more than it was for the heat of fusion. 40.7 kilojoules per mole.
No, it's not. Someone wants to. Hey, at least.
It's pretty remarkable when you think about how much energy this is for a change like that. A mole of water is not a whole lot of water, 18 grams. You can hold 18 grams in your hand. If you have 18 grams of water and you need it to boil, you've got to add 40.7 kilojoules of energy. That's 40,000 joules to boil that amount of water that you can hold in your hand. And you can easily hold that in your hand. You probably hold 2 moles of water in your hand. So it is a tremendous amount of energy. We had Freddie, you know Freddie, right?
Yeah.
For fun, Freddie calculated how much energy 40.7 kilojoules is. He said that would be about the equivalent of a normal-sized teenager running up 600 steps. 600 steps is a lot of steps. You'd use a lot of energy doing that. That's to boil 1 mole of water. That's how much you can hold in your hand. It's a tremendous amount of energy. So breaking particles apart, that takes quite a bit.
I see you do that. What? 6%. I'm terrified.
All right, now I have a little issue. The next several slides on my presentation have all been somehow deleted, lost. Whoops. So I have a PDF file with this. This is what I put on Schoology. So this is the next thing that I wanted to show you. This is a question out of chapter 10. Like several are assigned, and many of them have this kind of thing. The question is, how much heat would be involved in raising 500 grams of ice at -20? Yeah?
It's just me seeing things, or there's a graph actually.
Yeah, there is a graph. I'm going to highlight the graph in a second. I don't know why it didn't turn out well.
I thought it was.
Anyway, we have 500 grams of ice. Now, 500 grams is a pretty good-sized chunk of ice. If we wanted to raise that from -20 degrees, which is a good temperature for ice, up to 150 degrees Fahrenheit, that would be going through all physical states to get to steam at 150 degrees. how much energy would that take? I'm going to just go ahead and cover this up. Not cover it up, but trace it. This is a graph that's called a phase change diagram. It tells us what the temperature is as we add heat to it. Now we begin here at some arbitrary negative number, and as we add heat, the temperature goes up. As soon as the solid hits the melting point, what happens to the temperature? It just goes flat, doesn't it? So the temperature levels off over quite a long period while that phase is changing, and once all of the ice melts, then it starts to raise in temperature again. Now, in reality, in real life, if I have a thermometer that's stuck in the middle of a frozen block of ice, that's the best way to measure what the temperature that is. It is true that the water on the outside of the ice will warm up faster than what the thermometer in the middle of the piece of ice will notice. Does that make sense? So there's a little bit of just make-believe in this, because we're assuming that like all of the ice is the exact same temperature. It's really impossible to do. You can't do that. Because the part that's exposed to the environment is going to be heated up more than the middle of it. An example of that would be in the springtime, when it's March and April, and all the snow is melted except for those big piles of snow which the plow made. It takes like several days for them to melt. Sometimes weeks for them to melt. They get smaller and smaller, but even if the temperature is 60 degrees every day, you still got those silly piles of snow. And that's because the middle of the snow doesn't have access to that heat like the outside of the snow does, so it takes a long time for it to finally melt down. So anyway, I just wanted to mention that. Once all the ice is melted, then the temperature starts going up again. That's where it's liquid. And then it hits its boiling point and levels off. And then once it's all boiled, it starts going up again. So again, this is a phase change diagram in which we see the solid, the liquid is here, and the gas phase is up here. What are the temperatures that we care about? The beginning temperature is negative 20 degrees. At this temperature right here is where the ice melts, that's 0 degrees. At this temperature, the water is boiling, that's 100. Now, somewhere above 100, if I'm doing this to scale, call that 150. So we need to know how much energy it takes to get from here all the way up to there. Unfortunately, this is a loaded question, because when the temperature is changing, we can use Q equals MC delta T, like in there, and there. But when the temperature is not changing, you can't use Q equals MC delta T. So here's the way we would go about this. I don't know if we're going to have time. Hopefully we can actually get a numerical answer for this thing. Now, I'm going to break this up into how many different Qs do we have? We have Q1, where the solid is heating up to its melting point. Q2 is where the solid is actually melting at the same temperature. Then we have Q3, where the liquid's heating up. Q4, where it's boiling. Q5. 5 Qs. Could be worse, there could be 10, right? So 5's not that bad, I guess. Q1. The solid is warming up. We have a temperature change, so we have to use MC delta T. This C, you're tempted to use 4.18. No? It's ice. Ice has a different specific heat. Yeah, I'll just go with 2.1. All right, so yeah, we have the mass, it's 500 grams, we have the C, and we have the delta T. What's delta T? Just in this region, starts at negative 20, and that region ends at 0. So we have the delta T. Then we get to Q2, where we have the melting process. We have the heat of fusion, which I gave you the value of in the last slide, times the moles. You're going to have to find moles of ice from the 500 grams. That's not terrible. Q3, we have to go back to MC delta T because the temperature is changing. Where we have liquid water, that's where we can use the 4.18. That takes us up to the boiling point. Q4 is where we use heat of vaporization times moles. The moles there is the same as the moles in Q2. And then at the end, Q5 is again MC delta T because the temperature's changing.
What's the?
And the C in this case is 1.8. Steam has the lowest specific heat of all the phases. Girish, what was that?
Let's do all of this to calculate that.
Yep.
Nice.
Can you get an answer for that? One thing that I want to caution you about, I did this quickly last hour and got burned. I know, I don't like getting burned.
Wait,
Uh-huh.
like you got toasted places?
What's the unit you get for Q1? Joules. What's the unit you get for Q2?
Not joules.
It's kilojoules. Because remember, the heat of fusion is kilojoules per mole.
Oh,
So yeah, Q1, Q3, and Q5 are all going to give you joules. Q2 and Q4 give you kilojoules. Be careful with that.
Wait,
Mess up that
so
tank.
water,
Toasted you, Mr.
the heat of
Hi, Fred.
fusion for water is 6.01 joules.
No, kilojoules per mole.
How about vaporization facility?
40.7 kilojoules per mole.
Oh, you mean other
Yeah, so Q4 and Q2, those are going to give you kilojoules for the Q. But these, that say on the specific heat in joules per gram degree Celsius, the grams of degree Celsius cancel out, but the joules are the unit that we get for Q.
Wait a second.
Oh, so the N for water is 4.1 joules.
The C for water. M is max. C is 4.18 joules per gram degree Celsius. Yeah. So anytime you use this MCAT equation, your unit is going to be joules. All right, who can get the answer for that?
Wait, where'd you?
I'm going to try again because I failed last time. I guess I got to use this.
See that we tell you guys the story about how his brother's girlfriend burned up her hair.
What do you want?
We still have my hair to make
Dude, right up here is Matt and all the reviews. Do we even take the effort?
and hiding.
Oh yeah, Hadi soccer, bro. Remember that day, like, it's crazy run up there.
Maybe I'll give intermediate answers so we can keep better track of this. 500 times. So Q1, I'll just write this small above where I have the work done. I'll change everything into kilojoules. Q1 is 21 kilojoules. You got that? Are we up to a good start?
Oh no, my God. I'm telling you what he's saying.
Don't forget to change the moles for Q2. I get 100, I'll just round off 167.
167. Okay.
So you see it takes a lot more energy to change the physical state than it does to change the temperature. Depends on how big the temperature changes, I guess. Oh gosh, we better hurry. And then MC delta T for that was 500 times. The water Q is 290 kilojoules to get from 0 degrees to 100 degrees. And then 40.7. This is 1131.
Wait, what class?
Whew. Wow. Okay?
He went to do
Hey, study session tomorrow.
this I said. Oh no, I can't do
I did something wrong.
No, wait, that was on this side.
What's that, Dan?
Wait.
I got 45. How did you get 46?
No, it wasn't. It was 2 weeks ago.
Why did this week?
What?
Okay, so add those 5 together, and that's our answer.
That's what I'm asking.
I mean, it came out like 3 a.m.
So we get 1,573. That would be the, or so,